Welcome back to the session of real-time operating systems. So far in the previous sessions, what we had covered was basically about modeling a real-time scenario and how we are going to see a scheduling analyzer, and also how we are going to mathematically model the system. Now in this session, we are going to see about a task graph. Actually, one question we need to analyze, that why do we need a task graph first of all? Because a schedule is of course a set of tasks and we know the order and everything, but some internal information is required to be covered. Like for example, if you see in a task graph, generally a task where we have a set of tasks, either they can be independent or they can be dependent. The dependency can be due to several conditions. It may be a parent-child relationship, or the task itself may be split into some sequence. Something like if we have a set of operations, like it has to do a particular operation, and then based on that calculation it has to do some other independent task. So in such cases, what happens, task dependencies have to be monitored. Now when task dependency creeps into the scenario, there are three factors which we need to effectively monitor. Point number one, first we need to see the sequences being monitored. The task, for example, if task A, if we have a set of tasks, say if we have two tasks, say task A and task B. Supposing we need task A has to be executed first and task B has to, this sequence has to be followed. And second, the resource has to be divided among task A and task B. That is, whatever resource, say if we have 10 units, out of 10 units, 5 units has to be assigned here, 5 units has to be assigned here. So that we have to ensure that both the tasks get scheduled. For any reason, task B should not miss its deadline or not be scheduled due to inadequate resource. Similarly is the case of task A. This scenario will be most widely appreciated when we go for online scheduling. Supposing if we have a set of tasks which are arriving on the fly. In an offline scenario, we know all the set of tasks that has to be executed and we have the required resources. In an online scenario, what happens? Tasks arrive on the fly. So we require the resources to be properly distributed. For that, we require proper slack distribution algorithms and effective measures to monitor that. These are the two points. Is one is the order of execution needs to be monitored, and also the resource availability has to be distributed. The third factor is the scheduling cost in terms of computation and communication. Supposing we have a set of two tasks, like on processor 1, I am scheduling T1. I am not able to schedule the full task for several reasons. Say supposing this task has 5 execution units, and we have, if you see that the sum of the task utilization on this processor core is exceeding unity, or the make spans are large. So what I am doing is I am splitting this task into two, T1 of 3 and T1 of 2. Now the question is, there are two scenarios, either we migrate or we duplicate. Like supposing whether we migrate this task from processor 1 to processor 2, or I directly schedule this task 1 fully on processor 2. What is the advantage? If we analyze the advantage and disadvantage in both the cases, if you see, when we are migrating this task, there is something called as a communication cost. Whereas if you are going to simply duplicate the task, that's creating another instance of the task on the same processor core, what we have to do is there's a computation cost which is increased. So generally these tasks this has to be monitored. This factor comes into the form of a scheduling cost. Now if you look at a task graph, now what is a task graph showing us? Like we have a set of tasks. There is something called as data dependency. There is a control dependency also. When we have a control dependency, something is a set of branch of instructions that has to be executed. In that case, that branch has to be completed. So that is one condition. Secondly, the data dependency. Data dependency, if we see, there are 4 basic hazards. One is raw hazard, read after write. Secondly, we have something called as war, write after read. And we have something called as war hazard, write after write. The read after read case is not considered a hazard because the data does not get manipulated. So if you see that, what does it mean? It's simple. Like when you have to do a write, the operation of read has to be completed. Supposing if there is a condition of doing a computation of, say, T1 is doing this calculation. T1 is doing a calculation of 5 plus 3. This is the processor 1 is doing. Now when we are going to do the next condition, 8 plus 3, this result should be ready at that point. If supposing you do the calculation without seeing this result, the values are going to be inconsistent. So similar is the condition of write after read. When there is a write condition and then only the read should take place, the order should be maintained for this value to be reflected. Similarly, we have a write after write condition, war hazard, where the writes order should be maintained. So these three are the main data hazards. Similarly, when there's a dependency, the consistency has to be verified along with the condition. So if we see this task graphs, what information basically we gather is when there are conditional branches, when there is a sequence of data, in this what information we get is, we first see the earliest start time. We get the task start arrival time and the task deadline completion. We also get the data, the cost factor involved, whether it's the communication cost or the computation cost. The objective of an effective scheduler should be that to minimize this communication cost and computation. Now there's some measure called as, we have a measure called as granularity. Granularity is something which is defined as the ratio of the computation cost to the communication cost. So when we are doing this, when the communication cost is higher, that means the granularity is going to be lesser. Ideally it will be 0 to 1. It will be within a small value. So these are called as fine grained tasks. Similarly, if this communication cost is lower, we have a granularity greater than 1. So in this case, these are called as coarse grained tasks. So in an ideal and effective scheduling, if we want to minimize the communication cost, the fine grained tasks need to be scheduled first. So that information, the dependency can be analyzed using this task graph. Normally, we can use something called as Weibull distribution to get the randomness of the nature to fix the task randomly. Secondly, if you are going to do a coarse grain analysis, this all coarse grain tasks can be scheduled on a single processor core because the computation costs only tend to vary. It's nothing that migrating from one task, one processor to another processor. When we are doing this scenario, we have to see that when we are migrating a task from processor 1 to processor 2, how far the task has completed its execution. If it has exceeded greater than 50%, it's better that we try to execute the task on the same processor core, so to prevent the communication costs. So this is what actually we try to do it in an ideal scenario. If we are not doing this, whether to preempt a task or not, we'll be incurring a large amount of scheduling overhead in the scheduler. So this is the basic constraint by which we analyze based on the dependencies of a task graph. Thank you.